Very
Yes.
good. Excellent, thanks. Yeah, my presentation is on probing of quantitative values and abstractive summarization models. Let's see. There we are. So an introduction. So the paper explores the problem of hallucination and abstractive summaries of recent state-of-the-art models using novel probing methods. As a general overview, it proposes a set of 6 probing methods handling modeling of quantitative values, and it applies these probing methods to several abstractive summarization models that have achieved state-of-the-art performance in recent years. So essentially, let's launch into the problem. So this issue of hallucination, it's a term that's been used in the recent literature to refer to information that appears in summaries, in abstractive summaries, that are not information that's not present in source texts. And of course, this presents a problem with quantitative values where those values have critical significance. So for example, in finance or medicine, a numerical value is actually quite important, making sure that it's 100% correct and replicated correctly. And this affects a range of state-of-the-art abstractive summarization architectures. So some examples from Pegasus and T5, where they're trained on XSUM and CNN Daily Mail data sets. What you find is that these are examples of hallucinated values. These don't appear in the source documents at all, but they do appear in the summaries, which is not good. So the rationale for probing is using the encoder output as a representation of the input that we can then probe upon. So the idea is, so the encoder models the input document, then the decoder generates the summaries from the encoder output, the basic encoder-decoder architecture for abstractive summarization. However, if the encoder fails to adequately model the input, then this would be a potential source of hallucinations. In fact, a significant one. And so the approach followed in the paper considers trained abstract summarization models that are trained on the 2 most common abstract summarization datasets, XSUM and CNN Daily Mail. And then it compares these results against both randomly initialized and pre-trained baselines. Let's see here. There we are. And so the probing methods takes the original abstractive summarization model for each of the trained models. The weights are frozen, and then the probing model takes the encoder output as an input, and then tries to find values for the encoder's original input. In other words, it tries to replicate in a numerical form or in class form for a classification probing task, whatever the value was supposed to be that was originally received as an input to the encoder. 2 sets of float ranges are considered. So basically from 0 to 99.9, as well as 0 to 999.9. So 2 different test settings to see how the models behave with these ranges. Novel data sets of 10,000 training and 1,000 test data points are generated with specific text-based representations for each task. Let's talk about those text-based representations. So the 6 tasks, there are 5 regression tasks and 1 classification task. The 5 regression tasks are decoding percents, basis points, orders, ranges, and addition. Essentially, with, say, percents, it needs to find the decimal representation of that percent. It needs to regress to it. For basis points, the probing model needs to take the encoder output and be able to regress from that to the float-based representation for that value in basis points. Basis points, there are basically 100 basis points per percentage. Order decoding using a log-based 10 representation, so 15.3 billion should be replicated as its log-based 10 value. Ranges, likewise, it should be able to find those 2 values as a float-based format. So input is text into the abstractive summarization encoder. The encoder output is then fed into the probing model and into the probing module. And then these values need to be produced as the output of the probing module. Same thing with addition, except that these 2 numbers are then, the result has to be added together. And then lastly, the classification task, unit identification. It needs to get this input value, say 24.3 kilometers, and it needs to find the class for kilometers and identify that. So for results, for percents, orders, and ranges, the abstractive summarization models, their encoder outputs when probed do not consistently outperform baselines. In fact, in several cases, they actually underperform even random vectors. So say Pegasus trained on CNN Daily Mail or T5 underperformed in certain circumstances, as did say DistillBart. For the basis points experiment, the abstractive summarization models mostly outperform the baselines, but not always. So in some cases, the models do actually underperform. Say, several of them, for example, underperform even the untrained BERT. And we'll talk about that a little more in a minute. For addition, the models, the trained abstractive summarization models mostly outperform the baseline. So that's good news. Not always. So for example, say Pegasus trained on CNN Daily Mail again underperforms an untrained BERT model as a baseline. Unit identification, actually, we see much worse performance, especially with the 0 to 999.9 range. And the best, in fact, ties random vectors, and many severely underperform all the baselines. So you see that on the bottom right, just major underperformance. So the takeaways from this, the random vectors sometimes outperform the trained abstractive summarization models on the probing tasks. Especially as compared to, say, DistillBart trained on CNN Daily Mail. That one especially underperforms. The BERT models used as baselines, which are by themselves not pre-trained for to prepare for an abstractive summarization task, they often outperform the abstractive summarization models. So it outperforms T5, say trained BERT outperforms T5 trained on CNN Daily Mail on 8 out of 12 tasks. And the untrained BERT actually outperforms BART trained on XSUM, for example, on 9 out of 12 tasks. Ultimately, no model provides consistent superior performance, and the results raise questions about the standard pre-training and fine-tuning methods. So in conclusion, the paper considers encoder output representations as a potential source of hallucinations in abstractive summaries. And it introduces 6 probing tasks to explore encoder input representations of abstractive summarization models to determine adequacy and representations of quantitative values. And it finds that random vector representations perform better than trained abstractive summarization models on several tasks, but that non-abstractive summarization models often perform better than some abstractive summarization models do on these probing tasks, including randomly initialized BERT, which is of course untrained. And ultimately, no model provides consistent performance across the tasks. Very good, thank you.
Thank you, Nathan. Do we have any questions? I have a question for you, Nathan.
Yes.
So the accuracy that you were showing us in the results is quite high, despite that sometimes it's lower or across the baselines. So is that good enough for abstractive summarization to get confused with the numbers, or what are you expecting to see?
Okay, that's a bit of an open question. Essentially, so if I go back, so say, for example, with this slide with the hallucinated numerical values, here are values where the models did just generate examples out of nowhere. And in terms of these outcomes, essentially for the one task that actually uses accuracy because it's a classification task, if you excuse me, if you actually look down at, say, the 0 to 999.9 task there on the right, you'll see that some, like say T5 trained on CNN Daily Mail, performs as well as any of the baselines. But the problem arises when you see some others, such as say BART trained on CNN Daily Mail. Its accuracy was 44.3%. Now that's a substantial difference between that and say the result that we get with T5. So I'm not concerned about a difference, say, of 99.5% versus 99.4%. What is of concern is when you start seeing things like 43.3%. That's where the question's raised. Well, why, the bigger question of why this is happening. And so I'd say that that's the bigger concern. And so in terms of the question, what are we looking for? Excuse me. For say the RMSE regression tasks, I mean, a model that where the probing module can easily extract out of the encoder representations the values that are actually encoded there, all of these numbers should be showing 0. Like a perfect model would be showing 0 across every task. And so when these are performing, markedly worse than the baseline, and that raises questions about how it's gone about doing the representation. So say like on this slide for orders, you see BERT trained, which does not do abstractive summarization. It has a result of 46.643, the amount of error in terms of measured as RMSE. But then you look down and say BART, both of the BART abstractive summarization model types trained on XSum and CNN Daily Mail, you see we're comparing 46 against 268. So the representations, it's much harder for the probing modules to find what the original numbers in text format were for this task as compared to BERT trained. And so that suggests that there's an issue with how the encoder representations are modeling the text. I hope that answered your question.
Yes, thank you. Any other questions?
Thanks.
Any other ideas on how to improve the encoding?
Yeah, I think further exploration would involve there's probably 2 areas that need to be considered for improving the results. One is the process of tokenization. So because some models break up the numbers in ways that aren't consistent. So if you have a number, say 463.5, well, some tokenizers, given that each of these model types have their own summarizers, or sorry, excuse me, their own tokenizers that correspond to them because of the different methods they use. And some probably are doing a better job tokenizing over others. And that's one potential source of being able to improve. If we have a better tokenizer, that may improve results. A second area would be in the training process of the encoders themselves. It could be the case that the training data normally used in abstractive summarization is just gives insufficient coverage of numerical values in the first place.
Thanks a lot.
Thank you.